for each gate delays. Okay. As we all know that a hardware description language can be modeled using four modeling techniques. Those are switch level, gate level, data flow, and behavioral. Behavioral and data flow are the most used and high level description languages for modeling the hardware descriptions. And switch level is the lowest level, then the gate level is the second lowest one. The switch level, if we want to use the switch level modeling technique, we should know about the PMOSes and the NMOSes. So it is very difficult when we are going for the higher level of abstractions like combinations and sequentials. So we are not using presently the switch level. So after that, we may prefer gate level modelings. And in gate level modelings, as we all know, logical circuits are designed using logical gates. Same as like that, here the gate level modeling is defined using gate level primitives. In Verilog, there are some predefined gate primitives like AND gate, NOR gate, XOR, XNOR, NAND, BUFF, BUFF 0, 1, not if 0 and 1. So the basic building blocks of these logic gates, the basic building blocks for predefined gate primitives. So the syntax for gate instantiation is gate instantiation and gate primitives. Then if we are adding any delays, we can add delay, and then after the gate name and outputs comma inputs, we need to declare that. So these are the images of buff if 0, buff if 1, not if 0, and not if 1. For AND gate, NAND gate, NOR gate, XOR gate, and XNOR gate. For these gates, n number of inputs can be have and single output will be there. This n number of inputs also, it should be declared in between 4 to 5. Otherwise, the behavior of that gate will may gives the differs output than the predicted one. So we must give outputs in between 1 to 4. Then the behavior of that AND gate or OR gate will comes exactly as we want. So this buff if 0, 1, not if 0 and 1 are having three pins. Those are input pin, output pin, and one control pin. So this control pin works as enable pin. So using this, we can control the gate. So let us go with the gate level modeling of half adder. So in this half adder, we are using one XOR gate and one AND gate. So for XOR gate declaration, as we already seen that syntax for gate level modeling. So we should declare it as gate instantiation. So that here XOR gate I have used. So that I declare here as I can use 10 here for 10 it will not right now. Okay. In gate level modeling of half adder, we are using one XOR gate and one AND gate. So for declaring of XOR gate in gate level modeling, we are using this gate instant predefined instant name, that is XOR, and this is the instance name, that is X1. It can be anything as you want. So here we are declaring the input ports and output ports as outputs comma inputs. So sum comma A comma B. A comma B are here inputs for the XOR gate. And same as like for the AND gate, I am declaring as AND as a predefined primitive and X1 is the gate instance name. So C comma A comma B. C is the carry, is the output, and A comma B are the inputs for that gate. So gate level modeling can be done by using the help of structure of a combination of sequential circuit. So that it is also called as structural modeling technique. So here I have done an example for instantiation a smaller level program to the higher level program. This is like gate level modeling of full adder using two half adders. So here also I have developed a code for half adder. After that I have instantiated that to become to made full adder. So as shown previous example, I have given the predefined XOR gate and AND gate as a predefined primitives, and I designed half adder here. And after that, using this instantiation name, I developed full adder like module full adder. As for the outputs and inputs for that is sum and carry, A, B, C, or C in are the inputs. So I declared inputs and outputs, and whiles I have used it here like uh, here from A and B, this is the XOR gate 1. So I have used here wire 1, and for here for getting AND gate of A and B, I have used here wire 2, and after for getting A, B and C in, I have used here wire 3. So like this I had declared wire as W1, 2, 3. So for instantiation this half adder into this full adder, I have used this module name of HA, and gate G3 and G4 are the instantiation names or instance names in W1, W2, A comma B. W1 is here and W2 it will be here, and this is one half adder and this is one half adder. These both to combine we can get C out. So I have declared here like that. Here the first these two lines are instantiation of half adder 1 and 2, and for getting C out I have declared XOR here. So XOR gate 5 and C out comma W2 W3. So this is the example for gate level modeling of half full adder using two half adders. Uh, in gate level modeling techniques, there will be three delays. They are rise delay, fall delay, and turn off delay. So rise delay is nothing but the changing of one state to another state. That is the changing of 0, x, and z to the one level. So this is the gap is called as T rise. The time taken to rise from 0 to 1 or one state to another state. This is the T rise here. And the fall delay. The fall delay is declared as the state that change from 1 x z to 0. This is the this time gap is called as T fall. And turn off delay. Turn off delay is nothing but the changing of the values from 0, 1, don't care to z. So here it can convert to 0 to 1 or 1 to 0. So this is called as a turn off state that which gives the high impedance of z. So for the syntax for this gate level delays are gate as we know gate primitive. First we have to declare. After that with hash, using hash we have to define the simulation of delays, simulation time of delay. For example hash 5 like that. After that the gate name and outputs comma inputs. So let us see some examples about on this. See if we declare one delay, then it will be used for all. Means AND gate hash 5 A1 is the gate instance name, AND gate is a primitive gate, hash 5 is the delay I have declared here, and the outputs comma inputs I have declared. So here hash 5 means it will goes for rise delay, fall delay, and turn off delay. Means the rise delay will be hash 5 simulation time, fall delay will be hash 5, and turn off delay also will be 5 hash 5. So like that. So then note 2, it is considered as if the two delays I have specified in the syntax, then what will happen? So if two delays are specified, then it will goes for rise delay. The first delay will goes for rise, and second delay will go for fall delay. And the minimum of these two delays will get for turn off delay. So here I have given an example as AND hash 2 comma 3 a1 comma y comma a comma b. Y comma a comma b are the outputs comma inputs, and a1 is the instance name, and hash 2 comma 3 is I have given delay as hash 2 is for rise, hash 3 is for fall, and AND gate here is the gate primitive I have used. So it will go mm, two, the delay 2 is will goes for rise delay, and delay 3 will goes for fall delay, and this minimum of 2 is 2, so that it will moves for turn off delay. And note 3, if all delays are specified, then it will declare as rise delay, fall delay, and turn off delay. So in example 3 I have given AND gate hash 2 3 4 a1 and y comma ab. So here the
Yes.
AND gate is the predefined primitive, and hash 234i is given as 2 is given for rise delay, and 3 is given for fall, and 4 is given for turn off delay. So like this it will be the Verilog compilers will be taken. So the fourth note is default value of if you are not giving any delay, means we are not giving the hash only, so
Yes,
then
and
it will take the zero delay as default. So for an example, AND gate I have taken, and I have not specified any delay here, so it will take as default value is 0. So a1 is the instance name of that
yes,
AND gate, and y comma a comma b are outputs comma inputs. So this is all about gate delay,
yes, yes.
rise delay, fall delay, and turn off delay in gate level modeling.
Yeah,
So let us go.
you.
So next topic is additional level of control for each gate delays. Means for this rise and fall and turn off delays, we are having some additional delays. Those are maximum delay, minimum delay, and typical delay. So the syntax for this is gate level primitive name, and after that the specifications of the minimum delay is this maximum delay and turn off delay. This complete delay is giving further rise delay, fall delay, and turn off delay. So here also, if we specified one delay, then it goes for rise, fall, and turn off delay. Means uh, AND gate hash 1 is to 2 is to 3. We are using is to declare that it is a minimum delay, it is maximum delay, in it is the turn off delay for rise and fall, and also turn off. So this is like we are going to declare. And if you are giving two delays, if you specify two delays, then it will go this content, this entire three terms of minimum, maximum, and typical values will go for rise, and this three terms of 5 6 7 is go for um, fall delay, and minimum of these two will go for turn off delay. The minimum of these two is 4 and 5, so 4 will come as turn off, and 5 and 6 is 5 will come, and 6 and 7, and here 6 will come as turn off delay. If we specify all delays, then it will goes for individually as we have given it. Thank you.
Okay, you will start.
साला तो साइमन खत्म नहीं हो रहा.
Anyone finish it? If you're present in the group, if you are presenting in group, there also they give maximum 10 to 15 minutes in a group to present. So if you are presenting individually, there must be only 5 to 10 minutes. That's it.
We need to mention the in points, but in para also.
Usually PPT comes in points. I'll tell you later after this presentation as well.
चोद कहाँ ये?
Good afternoon, ma'am. Good afternoon, everyone. Today I am here to present my topic about data types in Verilog. These are the topics I want to explain now. First, introduction. Verilog is a hardware description language that plays a crucial role in design and verification of the digital circuits. It has abilities to model the systems at different abstract levels like gate level, data flow level, behavior level. It also supports the simulation. It provides us various types of data types including bytes, registers, integers. These data types define how the information is stored and how it is simulating. First, what is a data type in Verilog? Data type is a storage format having some range or type. Verilog supports only some predefined data types. They tell us how it behaves and how the signal is interacting with other signals. They, the data types can also impact to convert the design into hardware. It allows designers to specify the time delays, durations during the simulation. These are the types of data types: integer, net, register, real time, time. First, integer. Integer is a general purpose register data type. We use keyword integer is integer. It is used to perform the arithmetic and numerical operations in Verilog. It represents only signed numbers. Signed numbers means only positive numbers. If the size of integer is 32 bit, for example, integer a comma b, by the default, the size of a and b is 32 bit. The next data type is net data type. It tells the connection between the hardware elements. The keyword used to represent net is wire. For example, if we consider two gates and one gate output is connected to another gate, in the middle we use wire data type. By the default, the default value of net is z. For example, if we didn't assign any values for the variables, it by the default it takes the z. Z means high impedance. Net stores only continuous values. Next, register. Register is a data storage element. It used to store some values. The keyword used is reg. It stores only unsigned numbers. The default value of reg is x. X is unknown. The next is real. Real used to represent the floating point numbers. It doesn't have any range declaration. The keyword used is real. It is specified in a decimal form. The default value is real is 0. Next, time. It is used to store the simulation time. It represents only discrete time units. The keyword used is time. The width of time is 64 bit. Dollar time is system task used to represent the time during the simulation. Next, real time. Real time is also used for simulation time, but it represents the continuous time values. In the real time commonly used in Verilog for specifying delays. The keyword is real time and the default value is 0. Thank you.
presenting?
Full screen. Full screen. Full screen. Screen share also.
The screen share.
I am audible or not?
Hey, you speak.
Good afternoon, ma'am, and everyone. Today I will discuss in IC technology, history of IC technology and their usage. First, I will start introduction to IC technology. Uh, an integrated circuit is a small semiconductor-based electronic device consisting of fabricated transistor, resistors, and capacitors. Integrated circuit are building blocks of most electronic device and equipment. An integrated circuit is also known as chip and microchip. Also, then I will discuss IC invention. First, vacuum tube diode was invented by Jones Press Fleming in 1904, and vacuum triode was invented by Lee D. Forrest in 1906. Uh, then after this invention, Williamson, Shockley, and Berin and Breton in Bell Laboratories, he was voted transistor replacing vacuum tube in 1947. He was also a Nobel Prize in 1950 in transistor area. In July 1958, Jack Kegley of Texas Instruments invented integrated circuit flip-flop with second germanium, silicon, and gold wire, called, and it is also called father of IC design. First MOSFETs introduced by Kang in 1916, Bell Laboratories, from where start of a new era of semiconductor industry, and CMOS introduced by Frank Welles in 1963. We know that what is Moore law. Moore law is nothing but the number of transistors on the integrated circuit will be double every 2 years. Moore law is chairman of Intel Corporation. What is different type of circuit technology? First, BJT bipolar, and second CMOS technology, and by CMOS silicon oxide insulated and silicon germanium, gallium arsenide. Why we use CMOS? Yeah, because CMOS is low power. CMOS contain low power dissipation, high packing density, approximated equal to rise and fall time, scale down more easily, fully stored logic levels, and etc. And the scale of integration, a different type of integrated circuit. First SSI, second MSI, third LSI, fourth VLSI, and fifth ULSI, and last gradient large scale gradient integrated. First I discuss LSI. LSI in 1916, the technology was developed by integrating the number of transistors of 1 to 100 on a single chip. As example, gate flip-flops and operational amplifier also. And second, medium scale integration. In 1967, the technology was developed by integrated the number of transistor of 100 to 1000 on a single chip. Example, counter, multiplexer, adder, and 4-bit microprocessor also. Third is large scale integration in 1972. Uh, the number of transistor of 100 to 1000 to 10,000 on a single chip. Example, 8-bit microprocessor, RAM, ROM. That's it. And fourth is VLSI, very large scale integration. In 1978, it was come. The technology was developed by integrated the number of transistor of 10,000 to 1 million on a single chip. As example, 16-bit microprocessor and 32-bit also. A peripheral complementary CMOS. Fifth is ultra large scale integration. The technology was developed in the number of transistor of 1 million to 10 million on a single chip. As far as special purpose processor, and last
Please give me the number. What number it seems. It is
and last gradient scale integration. The technology was developed by integrating the number of transistors of above 10 million on a single chip. Today it is work also embedded system and single SoC, single system on chip. That's it. Thank you.
He covers it. That's it. Just wanted to finish it. You have break for 1 to 2. Do you have
Good afternoon, everyone. My name is Sai Ramya. Now I would like to tell about shift registers. This is the overview. Introduction. Shift register is a group of flip-flops used to store multiple bits of data. It stores the data in register. Here the register can move the bits in and out. That's why it is called shift register. It can move left side. It is called left shift register. If it moves right side, it is called shift right register. It is the types of shift register: serial in, serial out, serial in, parallel out, parallel in, parallel out, parallel in, serial out. Serial in, serial out. The shift register which give the inputs, which take the input serially and give the output serial, it is called serial in, serial out shift register. Here the below circuit consists of D flip-flop where the input is given serially and the output taken serially. Here the clock is given, it is a synchronous flip-flop. Next is serial in, parallel out shift register. The shift register where the input takes serially and we get the output parallelly is called serial in parallel shift register. Here the circuit contains the D flip-flops connected in serial manner and the clock is given common, so it is synchronous flip-flop, and here clear is used for reset the flip-flops. Next, parallel serial of shift register. Here in this we give the input parallelly and we take the output serially. Here we give the input parallelly by using the mux circuit. It is the mux circuit. Here the clock is given common and it is synchronous shift register, and here we take the output serially. It is parallel shift register. Here the input is given parallelly and output takes parallelly. Here we see each flip-flop. The output of flip-flop is not given to the next flip-flop. Here we give the input parallelly and the clock is common. So it is synchronous flip-flop shift register. Advantages: compactness, flexibility, low power consumption. Applications of shift register. The shift register are used for temporary storage data. The shift registers are also used for data transfer and data manipulation. Here by serial in, serial out and parallel in, parallel shift register, we get the time delay in digital circuits. Parallel in, serial out shift register also convert the parallel data to the serial data. Thank you.
Muted.
Okay.
So I guess only 1, 2, 3, 4 people have joined with their presentations, right? So what is called as presentation and what is called as what do people have did it? Online students, am I audible?
Yes, ma'am.
Yes, ma'am. So can anyone suggest like what are the things they have to improve in them? Improve in that presentation. Can anyone say what are the things they have to improve in their presentation?
The point should be more concise and the slide should be more dynamic.
Okay. Other than that,
Ma'am, in the slide, the diagram should be more, ma'am, rather than
Okay.
theory.
okay then. Okay then, other than that. So your first thing is your font size, the font style, what you're using, the background to your presentation, black and white. No, not only black and white, it might be any dark colors you must not use. It must be light colors what you're using. Okay, and your page must not be fully filled, like how Anand you have did. No, your font size must be small. It means for heading one for headline or title, you have to give one font size, and for the content one size. Your what happens in yours? You have given for all one same size. No, it should be different size. For body one size and for title one size. Okay, and then you have to add pictures. So if you are adding some diagrams or circuits or anything, you have to look into the circuit and then explain. Here, and coming to you both, you have mentioned it in a paragraph. So that must not be the case. You have to mention point by point. And if you are mentioning each and every point, you must not see to the points and read. If you are looking at the points and reading, or looking at the paragraph and reading, so what is the use of presentation? Correct? So whenever you're presenting, you must never see at least a single line if you're reading it. Explain what is there in the line. Okay, so one line you read and the next line you go to read. So this must not be this must not happen. You have to read the first line and then you have to explain what is the content in the first line. So as you in your presentation, many events were there, right? This event happened in this year. This they invented in this year. Just mention the year and what happened. That's it. And you have to explain who invented, what happened, and all. Here. So like this, you have to mention each and everything. Clear with this? So the difference of presenting and representing is different. So what you people all did today is presentation. That too, you have to improve in your presentation. You have to just, in a slide, you have to just write 2 to 3 points. Points mean sentences. Okay, and pictures, if you are adding, you have to see that and explain. Clear? This is called as presentation. And if you are doing your presentation single like individual presentation, it should be just like 5 minutes or 10 minutes, that's it. If you are doing it in a group, usually if you are going for any conference or anywhere, there they give just like 15 minutes to a group or 10 minutes to a group to finish it. Yeah, this is called as presentation. Coming to representation. So what is representation now? So what CMOS topic you have taken, data types you have taken, any topic. The first slide should be just a data types or CMOS or VLSI, any topic. Think we're taking a topic called VLSI. A topic you took VLSI, you have to see the just a single topic and you have to explain. So there no content is written on the slide. Okay, and then coming to the coming slides. The first slide is done, the second slide also. Title with 1 or 2, just a single point. Think data types are how many? 4 to 5 data types are there. So in one slide you write all the data types, real time and all. And from next you have to add only the pictures with a single sentence. And you must just see the picture and you have to explain. So representation and presentation both are different. So got the difference, online students?
Yes, ma'am.
Yes, ma'am.
So whenever you go to conference or IEEE projects will be there, if you're going there everyone do representation. Nobody do their presentation. So both things are different. For now, if you're preparing for presentation, that is well and enough. But going forward, please be prepared for representations also. And one more thing, don't see whatever you have written, don't see it and read. If you're seeing it and reading also, try to explain it what you have written there. Clear? Everyone, is it clear? So it is for everyone. I'm saying it once again. Whatever presentation you're doing, make it very clear, in short, and anytime anyone can come to your classes. I've told it, right? So yours is related to this with Verilog? No, right? So make any presentation which is related to your Verilog, CMOS or anything and keep it with you. Okay, prepare and keep it so that anyone can come and ask you to present. Clear? Is it clear for everyone? This presentation. No?
Ma'am, is there any certain size for headings?
Yeah, usually no, we keep it as 14, 16, 12. 12 is too small, but 12 is only for that if picture is written